Hello everyone, this is Group 14 Monkey Tracker Middle Term Demo. I am Evan Long, the computer engineer for this group, and my group mates are Lance Matarang, Nathan Villacampa, Joseph Galamidi, and all of them are electrical engineers.
The main project goal is to deliver a monkey tracker prototype capable of sending GPS location to the base station, which will then relay the information to a remote user system. These are our design specifications that were requested from the customer that we needed to abide to. The following requirements include a lightweight tracker, a 1 year service life, acceptable GPS accuracy, maximize the transmission range of research, more cost effective than the VHF telemetry tracking system that is currently used for research, able to send GPS data to a website remotely, and enclose the tracker and base station to protect our hardware in it. The, the ones that are highlighted in green are the engineering specifications that will be discussed in further detail later in the demo. Here is our generalized overview of how our system will be implemented when our design is complete. First, we will strap our tracker prototype to the monkey and make sure it is secured correctly. In different intervals, the tracker will transmit the GPS coordinates of that monkey's current location using the radio module of our prototype. That radio signal transmission will be then received from the base station's antenna, where it stores that information until later called upon. Finally, the base station will send that signal with all the information into our remote website, where it can be translated into Google Maps, where the customer can use that information for research purposes shown below. And here is where the information is, with the time of acquisition and location.
Our first requirement specification that we have achieved is average GPS location accuracy within 15 meters. Initially, we tested our GPS, the ORG1411 in Blanchard Park, and used a cell phone's GPS coordinates provided by an online website as reference. We quickly discovered that the cell phone's GPS values were not accurate at all. We witnessed errors ranging from 100 meters up to 470 meters and knew the phone GPS was the inaccurate ping by scoping out landmarks or shapes on Google Maps. We redid the test using landmarks as references. The image displayed has various red dots where we stood with the GPS running. This image shows how we measured the error distance from actual position to GPS coordinate position. The white dot is the actual location and the red marker is the GPS location. Here is a quick demo of the process and obtaining a fix at the location shown in the previous image. Here's the breadboard. You can see the Adafruit feathers connected to our custom GPS breakout along with a few resistors and an LED. We plug in the tracker and the code that was previously flashed onto it will automatically run when powered on. We'll make sure that the serial port is connected and the correct board is selected in the Arduino tools settings before opening the serial monitor. In the serial monitor, we see that the GPS is running and querying for a connection involving at least 4 satellites for trilateration. We don't immediately have a fix, but in just a few seconds, we already have time. This means that the GPS has already established a connection with at least 1 satellite. Normally, time acquisition and constant updates of time at a rate that mirrors real time indicates that the GPS will soon obtain a fix.
There we go.
There
You
is
got
the
it.
fix. We can see the parsing code provides us with latitude and longitude values in degrees and minutes, as well as the time of acquisition and the tracker tag. Here is a summary of 10 locations and their corresponding accuracy. The average error distance came out to be 11.537 meters, which meets our requirement specification. This value is slightly higher than it should be, primarily due to a few outliers that occurred in noisy areas, near buildings and urban areas. The next requirement specification is 447 meters of transmission range. Initial testing in a forest-like environment using 2 Adafruit feather modules yielded a max range of 480 meters, which meets the requirement specification. Recent tests, however, have yielded a max range of approximately 273 meters utilizing identical antennas and radio modules, but tested on UCF campus with clear line of sight and potentially crowded airspace. We are currently tasked with confirming 480 meters of range in a forest-like environment again to prove that the 273-meter range measurement on UCF campus is due to crowded airspace or some form of unnatural interference, but overall, for practical application in the targeted forest-like environment, this requirement specification has been met. Successful radio transmission will be demoed along with a GPS fix acquisition now. Here is the base station system power supply with LiPo batteries, solar charger voltage regulator, solar panels, and cell module stacked on top of the Arduino Uno that is wired to the radio module. Here on the left is the serial monitor that spams not available until a radio transmission at 915 MHz has been received. There is the breadboarded Adafruit Feather connected to our custom GPS breakout board. The 3.7 LiPo battery is plugged in, and the code is set to run immediately after the device is powered on. The blue flashing LED on the cell module indicates the module is connected to Wi-Fi, but in this demo it is not used. This demo was taken in the UCF breezeway under moderately cloudy weather conditions. The code is set to only transmit data if a GPS fix has been obtained, so the code queries the GPS until the relevant information can be pulled and proceeds into the radio transmission loop immediately after. At this time, Joseph, who is carrying the tracker, is moving around the entrance to the student union. As you can see in the monitor, we have successfully received 4 identical transmissions. The final requirement specification met is budget, where the total system cost should be less than $2,400. The current system involving VHF telemetry and manual tracking of the cotton top tamarins costs between $2,400 and $3,000. We are tasked with creating a cheaper system, and our total cost meets this requirement specification comfortably. The total cost of the base station system hardware and 6 backpack trackers is approximately $1,332 plus $3 a month for the cellular data plan. This value excludes the cost for the mechanical team's housings, as well as any application cost that the CS team may have, but the base cost for the hardware is significantly lower than the low end of $2,400, and we feel confident that this requirement specification has been met. No demo will be displayed for this part.
Although our breadboarded circuit is more or less performing up to desired specifications, our PCB is having trouble. Although we were able to bootload and flash our program to the device successfully, and all the modules have been confirmed to turn on and interact with the microcontroller correctly, we are experiencing a problem where the GPS is unable to acquire a fix and the radio can only send messages over extremely limited range. After confirming that the serial outputs from the microcontroller were correct, we felt that hardware had to be the problem and began testing the board. We have found that the current consumption from the board is far below what it should be at 17 milliamps for the radio, GPS, and microcontroller running. We expect more like 105 milliamps with just the microcontroller and GPS running. This leads us to believe that the converter is at fault and is incapable of providing the requisite current to our modules. Recently, however, we tested the converter by wiring resistors in parallel to the overall circuit. We found that the converter was able to comfortably output 100 milliamps to the resistors when attached in this manner. This leads us to believe that the issue lies with either the PCB or one of its components. It is possible that one of the components is being partially shorted out such that its total impedance is not being applied correctly on the power path. It is also possible that the power traces aren't functioning properly and are failing to deliver current. We have already tested the power pins for voltage and have found a healthy 3.2 volts on all those we tested. In the future, we plan to use an ohm meter to confirm the traces on a spare blank board that we have are behaving as expected. This would rule out a trace error. We also plan to do a side-by-side voltage comparison of our working breadboarded circuit against our misbehaving PCB circuit. We hope that these tests will be able to indicate where in the circuit the problem lies and that hopefully this issue will be something we can fix. We feel somewhat at a loss as to how to correct the present issues due to multiple factors. One, having reviewed the PCB file in Eagle, we do not see why the PCB shouldn't be working, which means that a redesigned PCB would likely be a very near copy of what we presently have. Two, we are limited on time now to remake a PCB. Three, The current is low for all configurations of powered on and off devices that we have attempted to run, i.e. even when running just the microcontroller or running the microcontroller and the GPS or the microcontroller radio, the current never exceeds 17 milliamps. This indicates that there is a shared supply problem between all the components, but we are struggling to think of what this could be. 4. We have already spent a significant amount on procuring the devices and modules for our PCB, many of which weren't cheap. Although we are being funded, we would still not like to continue spending money in this way. In summary, although the PCB is able to be coded and turns on its modules successfully when interfacing with the computer, we feel very uncertain about its ability to operate at full capacity by the deadline. In particular, it seems unlikely that the onboard GPS will be able to provide a proper fix due to the far too low current, or that the radio will be able to send messages at any sort of significant range.
For software challenges, the main software challenge we had with the tracker was the sleep mode and the GPS on the tracker. The reason why this was a challenge was because there was no way to see if the tracker's GPS was working when the tracker got out of sleep mode, since the sleep mode we were using made us not be able to reconnect to the serial terminal when we turned sleep mode off on the tracker. The way we fixed this bug was to use a radio receiver hooked up to another computer serial terminal and to use the tracker's transceiver to send the data over to the receiver to see the output of the GPS for the tracker. The other main challenge that we had was the connection between the base station and our CS team's website. The problem was that it was hard to set up this connection using @commands, but we later figured out a way to do this by using the web address of the website and uploading the data to their database directly from this web address. Moving forward as a group, we need to fix the hardware issue we're having with the PCB, and to implement a 24-hour testing period with the base station and the tracker. Then we need to make sure the connection between the base station and the website is still working, because the CS team is connecting the front end and the back end of the website together right now. And the last thing we need to do is to fit the tracker with the mechanical team's case.
With all these challenges, however, we are still confident that we will overcome those obstacles and will deliver a functional tracker in the weeks leading to the final presentation. The final presentation will showcase the full system overview previously mentioned with the mechanicals and CS's designs. Thank you for tuning in to our demo video.